in the morning from 8 to 10, and then I had another lecture. I put the tutorial on the lattice gas in Moodle, and with the notation which is identical with the notation in our yesterday's lecture. And we can shortly go through it. There are two things I would like to stress. The rest is not very important, but since we will return to this model several times, let us consider it again. So first, we calculate the number of different conformation, which is in this case of configurations. This is in this scale, in this case, the number of the microstates, W, which is the number of places, m factorial divided by n factorial and m minus n. There is again a mistake. M minus n factorial. Then we take the log of this, and when taking the log, we use the Stirling formula. Essentially, here in this example, we don't need the full Stirling formula. We could use our simpler approximation, which we deduced last time, and this is without 1/2 and with 1 instead of log of 2 pi. But these are all the fine things which do not really play a role in this particular case. And I see the hand.
Professor, I still have problems with this equation. How did we find out that the overall number of configurations is m factorial and n factorial m minus n factorial?
Okay, so this is what we discussed last time. Just let me. Do you want me to close? Maybe you want me to close this, and let me go. Ansicht. Sprecher. Can I remove? Okay. In reality, what I'm doing, so this yesterday we have drawn here the lattice and said that we have some cells of this lattice occupied by molecules. But essentially, the thing here is that you have M lattice cells. This is what you obtain after when you subdivide your volume, and you have N objects, which you have to place in these cells, and there is no possibility of repetitions, or there is no possibility that two objects occupy the same cell. This is how we take into account the excluded volume. Now, this is essentially, it doesn't matter that it's a lattice, it's simply you have M places or urns or whatever. And you have N objects, which you can place there. This is what we discussed. Now, how many possibilities are to place these N objects in M cells if the objects are indistinguishable? But first, it doesn't matter that they are indistinguishable. It matters essentially in the solution. Let us number the objects and place them. The first has M possibilities to be placed. The second one, for each of these M possibilities, has M minus 1 possibilities to be placed, because there are M minus 1 places left. And the last will have M minus N plus 1 possibilities to be placed. Is this clear?
Yes.
Yes. Okay. But here the objects are numbered. So I have the first, the second, the nth. First, this part is m factorial divided by m minus n factorial. Because I simply go here up to 1 and divide it, but what happens? Is this clear?
Yes, I think so, yes.
So what I do, look, I put here the following.
Yes, yes, I found it.
You have they divided by okay. Now this is the number of corresponding configurations for the case when the objects are numbered, and you can distinguish between first, second, third, and so on.
Yeah.
Now, in reality, the molecules are not distinguishable. They are all the same. You cannot number them. So now let us, for each configuration here, look at number of different permutations of molecules. So now I have here n places, and each place can be, so here I have the first, third, fifth, fourth, second. And then I have here third, first, fourth, fifth, second. For example, how many ways are there of renumbering of the objects? So it's very simple. The object which was first can get one of n numbers, can be renumbered by n numbers. So it's n.
Yes.
The number which was second can be renumbered by n minus 1 numbers, because 1 is already occupied by the first object. Clear?
Yes, yes.
And the last one cannot be renumbered because the rest is occupied. So that here I have n minus 1 ways to renumber the objects. If they are non-distinguishable, this means that this is exactly the number of different configurations I cannot distinguish. But they count differently here. So what I do, I divide this m factorial, m minus n factorial, the total number of placements, by n factorial, which is the number of indistinguishable placements which differ only by renumbering the objects.
Okay. Thank you. I get it now.
Okay, wonderful. Now we have it. And we return to our lattice guess. So we start from this formula, and for each of these factorials, this one is written wrongly. For each of these factorials, we use the Stirling formula. So I use the Stirling formula for this. I use the Stirling formula for this, and it's here. And I use the Stirling formula for this. This is here. And I write the terms of similar structure below each other. And now I see the following. These guys, from these three guys, two guys cancel. There is only one guy. All these guys cancel. I have m minus m plus m minus n plus n, 0. So only the logarithms stay, the terms with the logarithms stay. Now what I do is that I introduce the number concentration. I say that the number of molecules, so phi is the portion of the sites of the lattice cells which are occupied by molecules. So n is phi m. This is an auxiliary variable, but it's very useful, and I will always introduce it when playing with lattice problems. And we will see why is it useful. This is because at the end you get very, very compact expressions. So this is what I do. I say n is phi, where phi is the portion now of occupied sites, times the total number of sites or cells or whatever. And here I simply rewrite it. And then I put here this kb ln as a constant. It doesn't matter simply because it would be too long. And here I restore it. So now this is what I get. The prefactor is uninteresting because it does not depend on anything. And if in thermodynamics something does not depend on anything, it doesn't play a role. Because at the end you always take the derivatives. Now, what I do, I put down these logarithms. It's a logarithm of a product. I separate them. So I put down here, for example, ln 1 minus phi times m is ln 1 minus phi plus ln m. After I do this, I see that this term and the two terms which had ln m here and from here, they cancel. And now I see here a very compact and symmetric expression. It's symmetric against exchange of phi and 1 minus phi here. And now, look, m, which was here in front, comes outside of the bracket, and m is large. So if, okay, it doesn't matter. If m is indeed large, and the only thing I need when I'm doing my thermodynamics is that the system is large. When I'm doing my, so to say, coarse graining, the number of states must be large. Otherwise, thermodynamical approach does not work. It doesn't work for a single molecule. So, for a single small molecule. So this guy is always large compared to this guy. So I can simply neglect the guy. So I made two approximations. I will not make them next week. We will need to use the full Stirling formula, but essentially in a very similar approximation. But here, I first neglect the 1/2 because m is large, and then I neglect this logarithm. So this is what I obtain as my approximation for the entropy. The entropy, in reality, is a function of energy, number of particles, volume, and so on. Here it is expressed through the number of sites and this number concentration, but it doesn't matter because these are, for example, the functions of the volume. Now I will restore the volume dependence. This is here only the way to write everything very compactly. And the formulas like this, we will see them practically in any lecture, except this lecture, which I will give today, when we will be playing with the lattice models. So up to here, it's clear. Yes, it's quite straightforward. So we come from here to here as an approximation. Now we can get the free energy, which for a thermal model is a constant, U doesn't depend on anything, minus ST. So minus ST is this. And again, the constant I simply omitted doesn't play any role, the U. Now I would like to calculate the pressure. So now I have, there is a trick. I wanted to show the trick and then I decided I will not show it now. I will show it when I need it, because here it's simpler not to use the trick, but simply to substitute. M is volume divided by A cube. The number of cells is the total volume divided by volume of single cell. And single cell is chosen so that the molecule exactly passed in the cell. And phi is n divided by m. N is the number of molecules, so it's Na cubed divided by V. And it's also nice to look at this. NA cube is essentially the total volume which is occupied by all molecules. It's an excluded volume in my system. So now I put all this there. So I get an expression, and then I differentiate it. I hope you can differentiate. You can take a derivative. Just make this exercise. At the beginning, you obtain a length expression, but then everything cancels. And this is what you get at the end. It's a very simple expression. So it's kBt divided by a cube, logarithm of 1 minus na cube divided by v. So essentially it stems from here. The rest cancels. Very nice. Now I can do the following thing. How does the thing look like? It looks like very simply. First, let me expand this logarithm, taking the volume large, which means the concentration small. The Taylor series for this logarithm starts from minus x. Minus x minus 1/2 x squared minus 1/3 x cubed minus 1/4 x to the power of 4, blah, 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 blah. So the first term will give me kBt divided by a cube minus, so it will give me a plus, na cube divided by v, kBtn divided by v. This is ideal gas. Because any gas at low densities, which means at large volumes, behaves at ideal gas. And then I get the corrections to this ideal gas. If I bring this thing to the outside everywhere, I get the corrections in powers of the volume density, where volume density is n divided by v. And the corrections here, this has a dimension of volume, this has a dimension of volume squared. They all have the corresponding dimensions of volume to the corresponding power. And this is called the virial expansion. So these are essentially the virial expansion, the virial coefficients C. So we have learned two things. First, we have learned how to obtain the free energy for a thermal system. And second, we obtain this pressure, and we will have very similar expressions then, for example, for the tension of polymer chains, but it's too early yet to talk about this. And then we expand. One can do something else. So here, this expression is extremely simple, and it's considerably simpler first to get the result by differentiating, substituting, differentiating, expanding. But in other cases, which we will need, it's better first to expand and then to do the rest. And this is what I show here. So this guy, now phi is small. I have relatively small concentrations. This guy I can't expand because log phi, for phi going to 0, is singular. It grows to infinity. I cannot expand around the infinite value. I cannot Taylor expand. So there are tools, but I cannot do Taylor. But if phi is small, I can expand this. And this is exactly what I'm doing here. So I keep the first term as it is, and I expand in Taylor series this part, 1 minus phi ln 1 minus phi. This is what I get. It has different coefficients, 1, 6, and so on. One can differentiate and get the expansions. If you want, we can obtain the rest, because I can switch on Mathematica on this laptop, and we can see as many terms as you want. And I'm lazy to differentiate, although I can also differentiate by hand. So I put here the first terms. And the very first term is minus phi, and the rest are the powers with some coefficients. These are different from this, but it doesn't. So now I have this kind of expression. Now when I look at this, I see the following. And again, this exercise will repeat in different incarnations when will be considered the shapes of polymer chains, the osmotic pressure of polymer solutions, the phase diagram of polymer solutions. We'll do all the same tricks. So now I look here and I see this combination M phi, M phi, M, 1 phi comes to the outside, M phi, 1/2 phi, M phi, 1/6 phi squared, and so on. And this M phi is N, is the number of molecules. Now, the very first term is this, and this we have seen yesterday because it's the entropy of the ideal gas. Then the next term is simply Kbn, and it's constant. It only gives contribution to chemical potential. It's not interesting for anything else. So this is constant. This is the entropy of the ideal gas. And these are the corrections, which start from phi squared, phi cube. And N absorbed 1 phi, so it M phi, 1/2 phi. And what is phi? Phi is, if I go here, N A cube divided by V. So I put N cube aside, and I denote N divided by V as the normal concentration, number of molecules per unit volume. This is, I will call, volume concentration, essentially. So it's normal concentration of my molecules, concentration of the gas, number of molecules per unit volume. And this is the expression I get. All such expressions in forms of power series in concentration are called virial expansions. And the prefactors are virial coefficients. They are different because you can expand different value, different physical properties. The expansion of the entropy is different from the expansion of the pressure. But both expansions are virial expansions in terms of C, in terms of concentration, here and here. These coefficients, again, just like for the pressure, have a dimension of volume, volume squared, volume cube, and so on. The virial coefficients always have the dimension of power of volume. And now look how the entropy here looks like. And again, we will see such expressions continuously. It's some constant, which doesn't play any role. Then it's the entropy of the corresponding ideal system. This is a system around which you make the virial expansion. In our case, it was ideal gas. And then you have the virial terms. And the virial terms are due to interactions of the molecules. In our case, interaction is the existence of the excluded volume. And these are the things which all follow from this very simple premise, where essentially it's M minus N, sorry. And this is where I wanted to start. Now you will have it. I can make changes, but doesn't matter. Now we have it. And you have it in Moodle for your reference, because we will get very, very similar forms several times during the course. So you have seen now the simplest variant. Then we will consider the less simple variant with interactions with, I don't know. And now let me say the following. Let me remove this. Now you see the guy, you see my picture. And what I will continuously use in the lecture is the approach. Now I will go to the lecture, but first I would like to explain where do I want to come by the end of the day. So why I will do what I'm doing. So this is my lattice, which again is used for counting different configurations. And I would like to formulate, and I will always play with the lattice models of polymers, of single chains, of solutions, of melts, of whatever, at least in the first part of the course, which is about thermodynamics. And what is the difference between the lattice gas and the lattice polymer? The difference is that this is now a repeated unit, a monomer. It's a repeated unit of my polymer. I have a chain. It means that the repeated units have always to be the adjacent neighbors on the lattice. So I have less configurations than in the lattice gas because I forbid the gaps. At least in one direction, they must be neighbors. For example, a polymer solution is simply this is now molecule 1, molecule 2, and the empty sides symbolize the solvent molecules. So this is a lattice model of the polymer solution. The models work nicely, semi-quantitatively, which means that you can estimate the prefactors. And if you do them more in a more complex way than I show, even quantitatively, so you can predict the numbers, not only explain them, but predict. I will not go there because the aim here, we have, how much time do we have? We have less than 2 months. Is simply to give the understanding of how this modeling works. It's not really to make you able yourself to create a full quantitative theory of a whatever polymer system. Now, this is the lattice polymer model, which will work in the same way as my models for ideal gas or simple gas with only repulsion, noble gas work. So this is what I now what I have forgotten to do with my gas is the following. This is if I draw the volume, the pressure is a function of the volume on PW diagram. It's not yet now for polymer, it's for my. So here I have Na cubed, this is the excluded volume, the logarithms there diverges, so this is the pressure. And here the pressure goes as 1 over V, like for the ideal gas, and here it goes to infinity because you cannot press the volume, the molecules together. Okay, so now I must find the approaches to understand how to build lattice models for the polymers. And when we look once again, just before I leave my lattice gas, look, the first ideal term here for the lattice gas does not contain A, but the rest in the binomial coefficient, in the virial coefficient, they depend explicitly on A. So in order to get a more or less reasonable, even if not qualitative, but at least quantitative or semi-qualitative picture of my system, I need to be able to estimate this A, which I must put in theory. I will be quite happy if I will be able to make the estimate by the order of magnitude. But I will be unhappy if I will, for example, make an error by a factor of 100. This is not a theory. where there is a factor of 2, with this I can live. But if I am off by the orders of magnitude, with this I cannot live, because then I simply do not explain what really happens physically. So now I will partly repeat, partly reanalyze something you know about polymers, but my aim in the hind part of my head is to understand what is A, what kind of lattice model should I take for the corresponding polymer model. So now let me share my screen again. Let us guess. Do I have it here? Maybe I have a lecture here. Lecture 2. Now. And now let's have a look what happens. What happens here. So first let's simply talk what polymers are. But this you know, and this you know better than me. Many years ago, even before I was born, Hermann Staudinger discovered that there exists materials whose building parts are extremely long molecules. And these were polymers. He called them colloids, now we call them polymers. And they're typically long linear chains built of repeated units. This you know, because it's not your first lecture in polymer science. Now, these chains can be very different, but if you have a very long object, I have a very long object here, I have this cable. This is a very long object. At small scales, it might be stiff, but at large scales, a very long object is always rather flexible. So these polymer molecules are rather flexible. And moreover, you know, they live normally, not in vacuum, they live in a solvent. They are exposed to random impact of the solvent molecules, so they change their form, and at the end they form random coils. This you also probably know. Do you? Yes. Yes, good. Now, and here we will start, and we will start from very simple models. And what is, you have 100, it's a short polymer. It can be 10 to the power of 4, it can be 10 to the power of 6. So n is huge, which means now that even for a single molecule, the number of particles is so large that the thermodynamical approach is appropriate. So a single molecule is a macroscopic, essentially, complex system. And therefore you do not need anything except for thermodynamics. You don't need anything except for thermodynamics. If you want to understand the chemistry, you need chemistry, you need the atomic structure. But for physical properties of materials, this chemistry is absolutely not important and essentially useless. All things behave very similar. There are only very few parameters, so you can cook down everything to very few parameters which really govern the properties of materials. So here I simply have some examples. You can have side chains. You can have something which is quite bulky. You can have polymer brushes, which are very bulky. So this means that also the flexibility of the chains is very different. For example, the polyethylene molecules, it's practically almost a freely rotating model. I think you have already heard about freely rotating model from Mr. Rabe, or not yet? Unmute yourself when you talk.
Not yet.
Not yet.
Yeah.
So essentially, For example, with polyethylene, the situation is as follows. So what you have there as a repeated unit, I will only consider now, maybe I will give one homework on polymer stars, on dendrimers, but I don't know yet. So if you look at this polyethylene, it has a very simple repeated unit. You have a carbon atom, so to say, in the middle, and it's connected to two other carbon atoms with the covalent bonds, which are oriented like the bonds in diamond. So this angle, the bonds are extremely strong, and this angle is fixed. And then around you have two, so to say, two positions of hydrogen, and then you have the next thing. So the model is like this. And this angle, the valent angle, is fixed. It may fluctuate, it does fluctuate, also due to thermal motion by few percent, but around it, with keeping the angle, you can rotate. You can rotate here on a cone. And this is the valent angle model. So you rotate here. For polyethylene, there are three positions at which the energy is the lowest. The minima are not very long, very low. And essentially, you can even say how large the minima are. You can say it from the everyday experience. This we will discuss just a second later. But one can say that here you rotate not really freely, but quite freely. So there are three positions at which you feel more comfortable, but essentially you can take all of them. And you can also be in between. So if you have this E of phi, then there is some minimum, and the typical time is given by the Arrhenius law. Chemists must have learned about Arrhenius. Have you? Have you heard about the Arrhenius law? Who can tell me?
Yes, but like in kinetics, I think, as far as I remember, something we said.
This is true. This is simply the expression for the lifetime in some state if you know the energy barrier between the states. So this is how, this is the prefactor. You can essentially even calculate it, but it doesn't, it is not important. It's around 10 to the power of 11 for simple compounds here. And this is the energy barrier. So the lower the temperature, the longer you sit in one position. And now the estimate, this is also the estimates of the lifetime for different things. This is the background behind, you know, all this material testings under elevated temperature. It doesn't matter. But this simply means, now I told you can even estimate from the everyday life smaller. So here that it's definitely, I have the time scale below seconds. But if I freeze it, it will get stiff. You know that all this plastic stuff, plastic bags, get stiff at low temperatures. So you can estimate the barriers. This is where the thing loses its flexibility. But at normal temperature, the thing is flexible. Now, if I look at a polymer molecule, so here I see the atoms, this is the smallest scale, then I can see the thing as like this, like a flexible rod in the next scale when I do not resolve the atoms, and at very large scales, it's always the coil. It's something like what happens if you take a thread and throw a thread on the table or on the floor, and you know what happens with the thread. It always gets knotted and coiled and whatever. This is awful, and this is also what happens with it. Now, These are the flexible ones at high temperature, where you simply can say, okay, here it's not quite freely rotating, but let's approximate it by freely rotating. We can even forget about the valent angle, because a unit with 2 or 3 repeated units can essentially take any position it wants between the direction of initial bond and the final bond. There are enough joints to make it practically freely rotating. Now, another situation is with the thick chains. If you have a brush, or if you have bulky side elements, bulky, so to say, side chains, like, okay, polystyrene is not quite bulky, but imagine you have these rings everywhere. So this will be quite a bulky stuff. This will be not very flexible. So the free rotation at small scales is prevented by the geometry. Or you have something like this. Look at the DNA, which is a very bulky object. It is a double helix with relatively strong bonds between the two spirals. And moreover, it's strongly charged, which means that there is a Coulomb repulsion between different parts. So it's it's essentially a stick. But also this stick, although it's very hard to bend it at the very small scales, you can easily bend it at the large scales. And here there is another model, not more complicated, if you want, than the freely rotating chain. And this is the worm-like chain. This is for something which is either stiff or bulky. So here one looks at the following. I showed it here. Look at this part of the chain. I can draw it on the whiteboard. So this is my chain, and it's bulky. And there is somewhere a central line. And now I'm looking, so the chain has a beginning, somewhere it starts, I, its initiator. It's as if it started growing from that. And each point on the chain I can define by the contour length of this. So I go along the central line, and until I meet the part of the chain, the repeated unit I want to characterize. I call this the contour length, or the chemical distance. It's the chemical distance from the beginning, from here, until the part I would like to investigate. So now I start here, and I imagine that this is a vector along the central line at the beginning, or at some point of the chain. And this is this vector along the central line, the tangential to the central line. And now it has some angle theta with this initial vector. So this is a rotation of this tangential along the central line when I go along the chemical sequence or along the contour length of my chain from one point to another. Is this geometry now clear? Yes or no?
Yes, I think.
Yes. So what I do, once again, I take my DNA. This is the DNA, and here is the beginning. Yes, and then I say, at the beginning, this tangential vector shows like this. This is this finger, and now it shows like this. At this point, shows like this. And this is the corresponding angle. So I describe everything by this angle. And if I consider my chain as an elastic rod, just mechanically, under the influence of these random impacts, then the mean value of this angle decays exponentially with the contour length. Now, again, I can derive it from statistical mechanics. This is not my aim here, because my aim is much more modest. Just assume that, let's consider this as an axiom. Although it's a theoretical result, although you can also see this experimentally, doesn't matter. And how fast this mean decays is characterized by this L tilde, which is called the persistence length of the chain. So it shows how fast along the contour line the initial orientation is forgotten. Look, if the end part I'm looking at can be at a whatever angle, the cosine of a whatever angle in the middle, in the average, is 0. Cosine is between -1 and 1, and on the average it will be 0. So it decays to 0. At the beginning, the angle is 0 and its cosine is 1. So it starts from 1, and then the further you go along the chain, the smaller is this mean value. And again, one can assume, one can show, one can check that it decays exponentially, and this L is the property of the chain. So the bulkier the chain, the more charged the chain is, the larger this L. Now, at scales which are much larger than L, this exponential is practically 0. And again, the chain behaves as practically freely rotating. Now, what do I want in building? Now, I consider this, we will consider this model in much more detail a little bit later, but don't forget where I wanted to go. And where I wanted to go was to understand how do I have to draw my lattice model, for example, for a chain which at small scales look like this. And look, imagine that I have here a monomer or a repeated unit, I have here a monomer, or something I describe as a monomer. Yeah? Then, if the persistence length is large, the next monomer will be here. So I have, in order to be able to describe the configurations like this, I have to take the size of my lattice with which I then describe my chain to be of the order of the persistence length, at which it forgets its initial orientation. So this is a recommendation of how to take the lattice size, the step size of the lattice, or the step size, the effective step size of the chain. And now we will consider this in a little bit more detail. So, as always in theoretical physics, when you start, the best model you can use is the simplest one. So you start from the simplest models, and then you slowly go into the more realistic models, which are then either you have to do them numerically or they are useless. But the simple models are always very useful. So now let us imagine that I can describe my chain either on lattice or off lattice. We will see that it doesn't play any role, with something which is freely rotating. So off lattice, this is really something like this. So it's the size of my, now I wouldn't say repeated unit, because this is a step, so to say, of a chain. Or this is the characteristic scale at which it forgets its orientation, and the next part of the chain can take a whatever angle it wants with respect to this. So this is a freely rotating model. This is the off-lattice model because all angles are allowed. And I can consider also a lattice model, which I would prefer and which I would use mostly in what follows, where it can take this, this, this. So it can take one, for example, in my square lattice, it can take one of three or four possible positions. Now, in order to go further, I will look at two scales. These models, so this and this on a lattice, correspond to the class of random walks. They're called random walks. I will tell you a story why they're called random walks, what are random walks, but these are random walks. And essentially, seriously speaking, if I consider this as the molecule, it cannot fold on itself. Because if this guy would like to sit here, it will have to occupy the place where there is already something. There is an atom or a monomer there. It can't exactly occupy the same place. Whether this is a problem or not, it's a different question. But in the simplest case, I will forget about this random walk where the position can be taken at random, and I fully disregard whether there was a monomer or an atom or whatever there or there was not. I simply say everything is allowed because it's simpler. Now, what I have here is, for example, this is a freely rotating model where you can take whatever angle whatsoever, and then the same is on the lattice, there is no difference. And essentially, the term random walk starts or stems from Karl Pearson's question, or Karl Pearson's work from 1905, where he asked what is the distribution of the end-to-end distance. We will solve the problem next week. And this very small note in Nature was called On the Problem of Random Walk. And since then, the model is called random. Pearson needed it for his works on disease spreading, vector-borne disease spreading, malaria by flies, by mosquitoes, sorry. The model was essentially formulated 5 years before by Louis Bachelier as a model for financial speculations. And the model was, again in the same year, 1905, used by Einstein, essentially in his PhD thesis, in his work on the measurement of molecular sizes. This was the topic of his PhD. So the model is 115 years old, and really great, one of the most important models of statistical physics. So what I have is that the displacement, I start at the beginning, this is n equal to 0, R0 is 0, I start at the origin of coordinates, and then I make a random step. One typically said that there is a drunkard, and this drunkard makes steps, whatever. Pearson never spoke about a drunk man. He simply said a man makes a stretch of L yards, then changes his mind and make another stretch of L yards in whatever other direction. So this is the definition. Nobody spoke about the drunk man. So this is a step, and the direction of a step is taken at random. And then you sum up n such steps. If you are looking at the polymer, then Rn is the end-to-end distance of a polymer chain of such freely rotating units. Now, since they are freely rotating, the mean of R is 0, because the mean of A is 0. Is this clear? Because you can go in this direction exactly with the same probability as in downwards direction. So it's 0 for each of the terms. And if you take the mean of the sum, it's the sum of the means. So this must be clear. And now let's calculate the mean squared displacement. This is now something which will be very important. It will be continuously important. So now let me look at the mean squared. So the mean squared is essentially squared. This is this, this is my R squared, and then I take a mean. Now what I do is a trick. And this is a standard trick which we will reuse 10 minutes later in the integral representation. It works for sums and it works for integral. The square of a sum is a double sum. So if I take a sum and multiply it by the same sum, the only thing I have to do is to use a different index. Yes? Because I have A1, A2, A3, and here I have A1, A2, A3, but I have to take the products of all different A's. So it's a double sum of AI, AJ. You follow? Good, great. And in this double sum, I separate the diagonal and the non-diagonal contributions. So what does mean diagonal, non-diagonal? So if you make, so for example, I have the sum AI, AJ, let's say n is equal to 3. I from 1 to 3, J from 1 to 3. So it is
Professor?
A1 plus A1, A2 plus A1, A3 plus A2, A1, A2, A2 plus A2, A3 plus A3, A1 plus A3, A2 plus A3, A3. This is exactly what happens if I write it. And now look at this table. It has on its diagonal the products with the same indices, and off diagonal it has the products.
Excuse me, Professor.
Yes.
We cannot see the board. Like.
Sorry. So I am writing here this double sum for n equal to 3.
Okay.
And you see, if you put it, you fix this, and then first you do summation over j. A by 1, 1, 2, 1, 3. Then you fix it 2, 2, 1, 2, 2, 2, 3. And you have these diagonals with the same indices, and you have the off diagonals where the indices are different. And okay. Yes, this only explains the terminology, but then I separate the diagonal and the non-diagonal contributions. The non-diagonal I can only sum up over the upper or lower part of the table because of this property of the product that AI, AJ is the same as AJ, AI. Now, this guy, if all the lengths are the same, is simply the length. And there are n of them. It doesn't depend on orientation. It's a square of a vector. It's simply its length squared. This is this. And this guy vanishes because, look, this is independent from this, and this rotates freely for each orientation, there is an opposite, and when I average, I get 0. So this guy is away. Is this clear? Yes or not?
Can you explain it again, please?
I have two independent vectors because the directions of the two steps are independent. Yes? If they are independent, the mean of the product, AB, is the product of the means. They are independent.
Yeah.
And each of them is 0. So the cross term, the off-diagonal term, vanishes. And mean squared displacement, mean squared distance, mean squared end-to-end distance is simply the number of these independent segments or repeated units or whatever times the length of each of them. This is great. Now, this gives me the possibility to tell what is this A. Look, I rewrite this. First, what I see is that the root mean square. So I understand what is the square of the end-to-end distance. I can take a root of this, and this is my estimate of the size of the molecule. So the typical size of the molecule goes as n to the power of 1/2, at the square root of n. This is a very important result. It's true for my simple random walk model. It's not true for the cases when the excluded volume does play considerable role, because I neglected it here. We will see what happens when it does play a role. And in reality, there are both cases. So under some conditions, even the same molecules, under some conditions, they behave as simple random walks, and under other conditions, this self-avoidance is of primary importance. This we will talk about, but now we are playing with a mathematical model of a non-drunk man, so to say. We say we have these random steps, and we sum up the random steps. Now look. Now I have here, I can put this NA squared as LA, where L is the contour length. If I took my mean line, my central line of my chain, and measure its length from one end to the other end, or if I take my polymer chain and pull on it until it's fully elongated, until I orient all chemical bonds as far as I can orient them, I get this contour length. And then A is, and then R square is LA. So R, root mean square, is a geometric mean of a contour length and the length of a segment. So root of R is square root of LA. And then I can introduce this A by definition, because this is what I know. If I know the chemical structure, if I know what is the flexibility, what is the, so to say, characteristic length. This I can measure. I measure this in scattering experiments. And then I can tell you what is the L. And I call this the Kuhn's length. This is the effective segment length. This Kuhn length is exactly what I have to take as A, as a lattice spacing, when I build my lattice model of a chain. I have quite a reasonable estimate. This I measure, and this is chemistry. And now I have my lattice model. Now I make here a simple calculation, and then I will be ready for today. And I will calculate the Kuhn's length for a worm-like chain. There are some details in this calculation Not the whole calculation will be useful later, but I will refer to this calculation because some of details of these calculations are again repeated and repeated. And I always will show relatively detailed, simple things which you can calculate, which are reused. And if things are not reused, I will simply postulate them or say, and it's always like this, or illustrate them somewhere else, but I will not go into details. And here I will go into some details. So now we assume this model with the exponential decay of correlations, and the rate of this exponential decay is called the persistence length. And this model comes out essentially of chemistry and something Arrhenius-like. I didn't tell about this, but let's simply assume it as a model. For me, it's now a definition of a behavior of something I call a worm-like chain. I don't say that each worm behaves like this. I don't explain why the worm behaves like this, but this is my definition of the worm-like chain. Okay. I don't explain why a bulky and thick fat chain does behave like this, but let's do it. Now I will perform, but now for integrals, exactly the same trick I do here. And the first thing is to understand what is r, what is the distance. I first have to understand the analogon of this formula. Now look, let u of s be a unit vector in the direction of the chain. Now I will draw something. I will close this and make a picture. So what we were doing in our first, in the random walk, we were taking the sums. Sum of ai. And these a's were some vectors, and I sum all these vectors. And I sum them together with this is r. I sum them together with the directions, like vectors. And if I take the sum of the absolute value of r, then this is simply the contour length. This is my L, capital L. So this is for such a thing, for a discrete random walk. Now what I have is a continuous and essentially smooth chain. A chain is modeled by a smooth curve. And at each point, it has some orientation, a vector, a tangent vector, which is showing in some direction. Let me take this as a unit vector. I simply say this guy has a unit length and the direction which shows at the slope, which shows me the slope of the chain at this point. And then if I make a short step along the contour length, ds. Contour length is simply I take a thread, and on this thread I have centimeters. So it's like this thing which the tailors use, and I put it on the chain. And then I can say that this displacement A is u ds. It has length s and direction of u. Is this clear? And as soon as this gets clear, the total end-to-end displacement is the sum of these a's, so if you want the integral, and then what I have written here, now let me share the screen again with you, and then this holds. So here I have written exactly this. This is the sum of the very short steps along this continuous model of the polymer chain. Now I make the same trick as here. I have a square of the integral, which is a square of the sum. And now I put the square of the integral as two integrals, as a product of two integrals. It's a product of the sum or a double sum. So this is an exact analogon of what I have done for sums. And now I average. So I put this product of integrals as a double integral, and now I average. And the average of the sum, if the sum is the sum of averages, so I can average only inside of the integrals. And I know what this is. What is a scalar product of two unit vectors? It's a cosine of the angle between them. So I have here this mean cosine. But this mean cosine I already know from the definition of my worm-like chain model. I know this guy from here. I didn't derive it, but I know it, or I postulate it. This is my model. I play with it. So now I have to take such an integral. The first thing I do, I can immediately put here the exponential. I didn't put it immediately, but imagine you have here the exponential of s minus s prime minus s divided by L tilde here. Now what I do here is I separate this integral into two. I introduce a new variable, which is s prime minus s, this distance. Because essentially, then I can integrate over the distance. 1s is the coordinate of the beginning. So look. The second I will switch. Switch off the screen. This is my chain. This is 0, s equal to 0. This is the initiator of the chain. And now, look, this would be s. And here I have in blue s prime. This is black. Let me take blue or green. No, it's blue. It's blue, but it writes black. Doesn't matter. Then what is black will write blue. Sorry. It's also black. Doesn't matter. So these are the coordinates which were used at the beginning. And the cosine there depends only on this difference. And now I denote this by t. And now I have to integrate. In S, I go from 0 to L, but this t, the limits of integration at t do depend on where I am. If I am now at S, then t can change from minus s to L minus s. You got it? Have you? Draw the picture. If you didn't get it, draw the picture like I did. And then everything is simple. So now I have written it here. So I integrate in S in the first coordinate from one end to another. And in the second, the t can go from here to here or from here to here. And I separate the integral into two. And here I have these exponentials. Now I have double integrals, but if I can something, can you see? I think I didn't. Yes, no, of course you can't. Why? Now here. So this is I separated this integral into two integrals in t with the limits from here to here. It's from 0 to L minus S and from minus S to 0. And now I have these integrals, and if I can do something, this is integrating an exponential function. So this is the internal integral e to the power of alpha x dx is 1 over alpha e to the power of alpha x. So I put it here, and I take the integral in the limits here from 0 to L minus S, and here I take the integral in the limits from minus S to 0. So this is what I get. And now I integrate these expressions in S. So I integrate from 0 to L S, which gives me L, and I integrate this guy. What I have lost here is the prefactor, it's L. There is a mistake. I will correct it. There must be L in front, because when I integrate this exponential, this you know, the indefinite integral I have forgotten this guy. I will improve it. Quadrat integral. But I don't have mistakes here in the last expression. So here it's 1 over, it's L tilde, and here it's L tilde in front. So I have 2L L tilde when I take this, because I have L here and L here, and I have the rest. So this is the expression. This is my R squared. And now let's have a look what are the limiting behaviors. If the length is smaller than the corresponding persistence length, then I expand the exponential. This is small, and exponential is 1 minus LL, and then this quadratic term comes, and essentially R squared is L squared. And it simply means that at very short length, very short chains, like this one, they behave practically like a rigid rod. You can hardly bend it. But very long chains, if the length is much larger than the persistence length of my chain, this exponential is 0 practically. And what I get is 2 times L tilde L. So the Kunz segment length is 2 times the persistent length. And this is what I will have to take as my lattice spacing in the lattice model of the corresponding chain. If, for example, for whatever reason, I would like to make a lattice model for a DNA. At scales which are much larger than the persistent length, all polymer chains behave very similarly. We will see the differences in behavior of very flexible and very stiff chains. I will then comment on it. But the approach to mathematical modeling of this situation is absolutely identical. The behavior can be different, but the approach is the same. And this was the reason of showing these standard things, because starting now, I will do nothing except for building and solving the lattice models. So now I stop the screen. I will correct the errors or mistakes in the lecture and then put a new variant on the net. You solve the homework. if we succeed, I will ask my student helper to put a folder which opens automatically when you are supposed to submit your homeworks. If we don't succeed this week, it doesn't matter, then we will simply discuss the homework. The idea that I will count your homeworks it's only to force you more or less to submit them, because I know what happens when nobody does anything. And the less the number of your attempts then to pass the exam, the easier it's for me. So this is the only reason. I will look at them. This is very useful for our discussion, but the marks I give, if I give any, they don't have any relation to the final. So it's okay. So now let me first repeat that if I will be late for our meeting next Tuesday, just wait. It simply means that my other meeting, which is also on Zoom, is not yet finished. And since I have only one computer with a camera, I have here my mainframe, but it doesn't have any camera, and essentially is secured like Fort Knox. Since my laptop is the only computer I have which has a camera, I cannot be on two Zoom sections simultaneously. Just wait, and then we start. And see you next week. Thank you so much for coming. I enjoy it. Bye.
Thank you. Bye. See you next week.
Thank you.
Thank you.
Thank you.
Yes, homework is for half an hour, but bye. Okay, bye.
Thank you.
Thank you.
Bye. You are welcome.